right, so today we're going to talk about the concept of energy conservation. Now, what that means is when we think of the word conservation, we're thinking of saving something. So what this concept talks about is how energy is saved through all of these processes and transformations that we've been talking about so far. So, energy is constantly transforming from one form to another, but it never just disappears. Okay. So, for example, if we're talking about that roller coaster example again, you start with lots of potential energy at the top of a hill, and that is converted into kinetic energy as you go down the hill. We'll talk about other types of transformations a little bit later in this section and stuff, but the general idea is that energy is always going from one form to another. It's not just going to disappear, it's not just going to go away. Now, it's also not just going to come out of nowhere. So the law of conservation of energy tells us that energy cannot be created or destroyed. So it can't just come from nowhere. It's got to come from somewhere. And it doesn't get destroyed. It never goes away. It's only changed from one form to another. Okay. So potential and kinetic energy are usually the ones that we talk about when we're talking about energy conservation, and they are constantly transforming back and forth. If we think about all of those different kinds of energy or those forms of energy that we talked about in the web quest and in the last set of notes, there's different kinds of potential and kinetic energies. So, for example, electrical energy is a type of kinetic energy because it's the movement of electrons. Chemical energy is a type of potential energy because it's energy that's stored within chemical bonds. So when you change from one form to another, you're still changing between a type of potential and a type of kinetic energy. So we constantly see a transformation back and forth from potential to kinetic. We never see the energy just disappear and go away. Most of the time during this transformation, some of that energy is turned into heat or thermal energy. Other times it may be turned into sound energy or light energy, and in that case it's what we call transferred out of the system. So when something like, let's say, a ball rolling, for example, a ball rolling down like an incline or a hill or something, it's got a lot of potential energy up at the top of that hill. But as it rolls down that hill, it's gaining kinetic energy. That potential energy is turning into kinetic energy. Okay, so the same amount of potential energy it had at the top of the hill is going to be the same amount of kinetic energy it has as it goes down the hill. However, that's not always 100% the case because we have all these other kinds of energy that it may get turned into. So heat is usually the most common example. So anytime that two objects rub together, you get friction, right? So when you have friction, you can feel this if you like rub your hands together really fast, they heat up, okay? Anytime that there's friction, some heat is going to be released. So there's obviously some friction between the ball and the ground that it's rolling on, so that creates a little bit of heat. So some of that energy is transferred out of the system as heat. That's why eventually that ball comes to a stop, because it loses some of that energy that it started with to the form of heat. It's not going to all 100% stay kinetic energy the entire time. However, the total energy of the system will remain constant. So whether that form of energy is potential or kinetic or thermal or chemical or whatever it is, the total is going to be the same. So we can write this as E, the big capital E stands for energy. So the total amount of energy is equal to the amount of kinetic energy plus the amount of potential energy plus all those other dissipative energies is what we would call those, the ones that get released out of a system is what it's usually called. So plus the amount of heat energy, plus the amount of sound energy, plus the amount of light energy, and so on and so forth, all those other kinds of energy, all of those will always add up to the same total, no matter what. Okay. So generally, we don't include those dissipative energies, so like the heat, sound, light. Okay, usually those amounts are low enough that we can kind of just ignore them, and we can simplify this formula to be a little bit easier to use for us to quantify and understand energy in a system. So we can simplify that formula to the total energy, so E total equals the kinetic energy plus the potential energy. So for the most part, this is how I would like you guys to think about total energy when we're talking about total energy. It's going to be the kinetic energy plus the potential energy. Okay. So since the total energy of a system is constant, if you know one of the values that's needed to calculate kinetic energy or potential energy, you can kind of rearrange this formula in order to figure out the other. So that kind of probably doesn't make sense right now, so let me show you here. So if we take our potential energy amount is always going to be equal to our kinetic energy amount, okay? That's never going to change, okay? So the one is always going to be equal to the other because they're constantly transformed back and forth. So we can change that into, substitute the actual formulas themselves into those values. So we can take our potential energy and substitute in our formula for potential energy, our mass times gravity times height. Okay. We can set that equal to our formula for kinetic energy, which is 1/2 our mass times our velocity squared. So we substitute in both of those formulas, and then we take away the stuff that they have in common on each side. So on each side, the masses will just cancel each other out. So we can get rid of those mass values there. We don't have to account for those. So we can simplify that even further. So gravity times height will be equal to 1/2 the velocity squared. So if you know a height of an object and it's asking what the velocity would be or what the kinetic energy might be, you can still calculate that as long as you have one or the other. So this is going to be a super helpful formula when we're talking about energy transformations. We're going to do a little bit of practice with these over the next couple of days. So this is one that you're going to want to get used to using and get used to seeing, along with this total energy equals the KE plus the PE. Okay. So tomorrow we will go into some practice with these formulas. So for right now, I just want you guys to get the concept down that the total energy is going to be the same. So the amount of potential energy that you have at the top of a hill is going to be equal to the amount of kinetic energy that you have at the bottom of that hill. Okay. So that's the end of today's notes video. Make sure that these notes get filled in your actual physical note packets, and make sure that all of the questions throughout this video are answered. And don't forget to hit submit at the very end of this video so your grade is recorded for it. If you have any questions, please email me, and I will see you guys tomorrow.